Potential dividers are really, really helpful if you have a situation where you need a varying amount of resistance, and like a rheostat kind of, you have these in your house where, there's a little lever that you move back and forth and you can change the brightness and the dimness of light based on, the time of day. Um, this is a setup where we have a metal bar here in the middle, and this bar is a conductor, and then we have a light in this case. It doesn't have to be a light, this could be other things. And we have this where we can move this back and forth. So, for instance, if we have it set up here, this would be the same as having a light bulb and part of this metal in parallel together, and then having this in series with it. If we need more resistance, we can move this over here and we can just slide it over, and then it would be like having this. We would have this and this in parallel together, and then this would be in series with it. Or we can completely bypass it and have the current pass through the light bulb, then through that. And it allows us to have, a different amount of that voltage used up in the divider. And again, this can be helpful for, a situation where we need a variable amount of current going through a particular part. So what we're going to do here is we have a potential divider that's 2 meters long. Every 10 centimeters has a resistance of 1 ohm. If a 15 ohm motor is hooked up in parallel to the potential divider, how much power does the motor use if the circuit is set up so that the divider is halfway down? And then how much power does it use if it bypasses it? So let's go ahead and draw this out. We have our motor, and then we have our length here set up where, it's halfway down. And I'm going to have you try this one. You're going to work this as a complex circuit, and then you can figure out the power. And then once you do that, you can try part B as well, where it's basically the motor and then the whole bar in series with it. So yeah, go ahead and try that, and pause the clip and give that a shot. And then when you're ready to check, you can hit play to continue. All right, so 100 centimeters long. Every centimeter is 10 ohms. Well, I'm sorry, every centimeter has 10 ohms, and it's 2 meters long. So if it's 2 meters long, it's 100 centimeters. So every 10 centimeters has 1 ohm of resistance. So we have 100 centimeters, which would be 10 ohms, and then that side would be 10 ohms. And so this is essentially the picture what we've got. We've got a a motor that is 15 ohms. We've got this, which is 10 ohms, and then this, which is 10 ohms. The first thing that we're going to need to do is bring the 5 and 10 ohms together. Those together end up being 6, and then we can bring them all together for a total resistance of 16 ohms. And we can set up the current, and I forgot to give you the current. And the current is 20 volts. And so we've got that. And then, and we can figure out the current 1.25 amps. And then we can go back one step and figure out how much voltage each uses. 7.5 in there, and we're just concentrating on the motor. So both of these, the bottom and the top, will both get 7.5, and the current passing through would be 0.5 amps. So we know the current, we know the voltage, and it's going to be using 3.75 watts. So if it completely bypasses it, we're going to have a situation like this. We'll have 15 ohms, 20 ohms, which is because it's 2 meters long, and every 10 centimeters has 1 ohm. So that's 200 centimeters, which would be the 20 ohms there. We add them up in series to be 35 ohms. We can use Ohm's law to figure out the current going through 0.571. So we've got the current passing through, and we have the resistance there. So we can find the power, and so it would use 0.89 watts instead of what we found before when we used the potential divider. So Kirchhoff's current law is very helpful for us, because as we move now into other circuits, This is going to be important for our understanding here. The sum of the charge entering a junction should equal the sum of the charge exiting the junction. We've actually been assuming this for a while here. If we've got 0.93 amps flowing through here, and that 0.93 amps comes to a junction, that's going to split. In this case, it splits into 0.39 amps and 0.5454. Now, both of these are going to come back together, and then so as it exits here, it's going to have the same. It'll have 0.93 amps, as it comes into the junction and then as it leaves the junction. So if we take a look at this circuit here, let's say we have a 12-volt source. We have a resistor that's 10 ohms. This is the depiction of the way it'll look like in a for IV notation, above kind of a box look in there for a resistor. We'll set up our starting point here. Basically, what we're going to be doing in this section is using Kirchhoff's loop rules. And this is a really helpful technique, especially as we get into more than one voltage source, where we really have to use this technique here. So we have our starting point, and let's say that the current is going around this way. We'll say that the current is flowing around this way. This is the positive terminal. And let's say that we want to set up our loop inside. So we're going to set up our loop inside going this way. What we're going to do is we're going to add up the voltages along the way. That's the first thing that we're going to do. So if we start from our starting point and we're following the purple here, we're going from the negative terminal to the positive terminal. And when we do that, we're going from the negative to positive. So we're going to add up 12 volts there. Going from the negative to positive side, so we're going to count the voltage as positive because we're going in that direction. So we have that, sum of the voltage plus 12. Next, we're going to go through a resistor. Now, as we go through this resistor, we're saying that the current is going this way and the loop is going this way. And because it's in the same direction as the loop, we're going to say that this resistor is using up some of this voltage, and so it'll therefore be negative. So we'll have negative 10, V from V equals IR from the Ohm's law, negative 10 times I being the current passing through. So Kirchhoff's loop rule states that the sum of the voltage will add up to be 0. Once you get back to your starting point, they should add up to be 0 because all that voltage river is going to be used up. And so therefore, the power delivered to the cell is current times voltage, and then the EMF there times voltage. Power used is I squared R. And power equals power is used up in the resistor. We can cancel from both sides. And in this case here, we can figure out how much is used up there. For our case here, we have, the sum of the voltages is 0. We can bring the negative 10 to the other side. So there's going to be 1.2 amps of current passing through. Now, this is a very, very basic example starting out to see how this works. And if we did this, like we normally have, we know we've got a voltage source, we've got our resistor, we can figure out, what's going on. In this technique, we're going to just kind of build from that as we go. Let's go the other way. Let's say we know the current's going this way, but we're going to make our loop go the other way. And we can do that. We can choose the direction of our loops, and we'll do that. So first we encounter a resistor. Now, in this case, we're saying that the current is going around from, in a clockwise manner, but our loop is going counterclockwise. And so if we go through a resistor in the opposite direction of current, which we are here, we're starting here, we're coming around, then we count the current times the resistance is positive. So we've got that. Now the next thing that we encounter is the cell. As we go through our loop, we're going to experience the positive terminal, then the negative terminal. And because we go from the positive terminal to the negative terminal, we're going to have a negative voltage. So negative 18. And so the rule is if your loop is in the opposite direction of the current, and the loop is in the opposite direction of the voltage source, for going from a positive to negative terminal, that's negative. And you'll see that we'll get the same thing, 1.8 amps with the 18 volt source. I think the last one actually had a different voltage of the source. We could have made this 12 as well, and we would have gotten 1.2. So yeah, so you can see how that works.